All right, folks, a very warm welcome to all of you to our course, which is MLOps and LLMOps and one new kid on the block, prompt ops. It turns out that the subject is evolving so fast that these have become specializations within what used to be DevOps. So in this course, we are going to cover all of that. It is a fast-paced course. You will find that we'll cover a lot of territory as we make progress. Before we continue, I need to apologize. I have a sore throat. For those of you who are physically present, rest assured I've taken a COVID test and I'm not sick. I also don't have a viral, don't have a fever or anything, but it's some allergy that's been bothering me for a few days. Now, let me just mention that today is the first day of our fall session. We are starting with a pretty rich buffet of courses. We have the boot camps, LLM1 and LLM2 that you all are familiar with. We have the Introduction to AI broad course. Now, if you notice these courses, MLOps, which we are taking, fine-tuning will start later in October. AI agents is starting now. If you notice, two things have happened for the courses. We have doubled the frequency of the sessions. So if something was once a week, we have made it twice a week. The second thing we have done is extended the duration of the courses. So instead of 3 months, they are 4 months. And instead of 6 weeks, they are 2 months. So we literally have not just doubled, but significantly increased the scope and the amount of material that we'll cover and the time we'll spend with you. There is another thing that we have done. For going forward now, we have a faculty of a teaching team, training team of many data scientists, many AI engineers. They are here in the audience. At some point, I'll introduce them to you, or I'll let them introduce themselves after some time. I would strongly encourage you to take their help as much as possible. In this world where most courses are offered through Coursera or through videos or through all of these channels where you don't get personal attention, we pride ourselves in being old-fashioned, mentorship and very high engagement based courses. The people you'll engage with are not just professional instructors with English majors here picked up some slide deck and are teaching you the topic. These are all seasoned data scientists. So with that, I would like to go into the course itself. Now, a few things about the course, the mechanics of the course. People often ask, like when will we meet and things like that. We, of course, will meet Mondays and Tuesdays. Monday session I'll be holding. Tuesday session will be remote only. It will be held by the TAs, by the team. They will take you through the labs and through a discussion session, and they'll give you help. I don't know what's up. I was perfectly fine in the other room, and the moment I've come to this room, I'm now having this allergy. So I apologize for that. So one thing, do come to the course portal. We are going to post a lot of material to this portal as we make progress. Slowly, it will emerge. It doesn't mean that all the material is there. You can see some of them are blank. It is deliberate. We don't want you to jump ahead. We want you to keep pace with it. But today, two things are important. Once you enroll in the course, you take these two different Zoom links. First Zoom link is where you are enrolled in now. The second Zoom link is for discussion, which will happen tomorrow. Now, we have posted the first week's lab. I'll encourage you to go to this lab and download it. This is a starter lab, and we'll talk more about it in the course of this discussion. Now, you'll find a lot of useful links like awesome LLMOps. This is a lot of people on the internet. They take a lot of time to curate the best resources. These are indeed the best resources that people have put together. I would highly encourage you over time to go and check out this list. If 3.6 thousand people have liked this resource, obviously much effort is gone in putting this together. There's another one also very much liked. In fact, as many as 16,000 people, 17,000 people have liked it. So it is here. You can refer to it later. I won't go into that for now. Now, what I will do is in this course, I'll just give you an overview of the journey. In every course, there are two tracks. One track is the leadership track. If you feel you won't have time to do the assignments, then you should opt for the leadership track. Leadership track is for strategic thinking. Something around here is causing me.
Has to do on 420 or something.
Actually, I appreciate that. I don't know what happened. It's perfectly fine. And the moment I sit here, okay, I apologize, guys. The leadership track, you should be only if you are in a director or VP or you're an entrepreneur, you have no time to code, but you're going to lead engineering teams. In such a case, we have a lot of case studies we'll give you, and we'll pose it as a real problem, a decision making that you'll have to do in your workplace. Should you use this or that? What is the trade-off of each of the decisions that you will make? And we'll give you some perspective. This perspective comes from a lot of experience. It's quite valuable. The second track is the developer track. I expect most of you to be in the developer track, which means that we are here to pull up our sleeves and to build something real. Now, the way we will do that is a little bit interesting. You will get a project. If you download this code, this zip file, archive file, open it up on your machine. Our teaching assistants will help you to set up your environment properly, your Python environment and so forth. And that brings me to the topic that Python is a prerequisite. But remember, this is a MLOps class. Thank you. MLOps class, which means you don't need to be a guru of Python. The kind of Python we need, you can pick it up. And most people pick it up in one day, at most 2 days. It's easy stuff. And our TAs will give you pointers on how to pick it up. The other thing I would say, for communication, we use Discord. If you see my screen, you will see that we have MLOps, and the topics here closely mirror the topics that you find on the course portal. This is to have a very organized discussion on each of these topics. Now, in these channels, whenever you post a message, our team is going to take these messages very, very seriously. And they will respond to you either through messages or they will get into a Zoom call with you immediately and help you along. So the main value of a course like this is that you have access to so much direct mentoring and help. So avail of that. With that in place, I'll go into today's topic. So, Patricia, are you adding all the people to Discord?
Yes, Asif. I think a couple of members haven't joined, such as Vasanti. So I haven't been able to add her. But rest of the people have been added. Yeah.
Okay.
Apart, I think.
How about
Yeah.
this? You send put a Discord invite in the Zoom chat.
Yeah. Yes.
So they can all join that. All right, guys. Again, I apologize for this unexpected energy. So now let's get started. This is whatever you are seeing, you have now. If you download that zip file and you open it up and you run in your machine, you will see that this project shows up before you. We try to create very well-documented projects. So as you can see, the project that we are giving you comes with its documented. Right? So once again, welcome to the MLOps, LLMOps, and PromptOps workshop. We are going to do a lot of fun things, but how are we going to do that? And what is MLOps? And why does it matter? People often underestimate the value of MLOps, especially the developers. To developers, writing a lot of code is to be the hero, right? So they feel that they're Atlas carrying the worlds on their shoulders if they write a lot of features and functionalities. And as AI engineers, if they build models which show good performance. But actually, in this field, it is extraordinarily easy, actually, to make a proof of concept. Anybody can go to Hugging Faces, download a model, 20 minutes later, voila, you have a working prototype. Now, that prototype just works. But the difference between that prototype and something that you can build a company around or something that you can take to production is pretty much the difference between a lightning bug and a lightning. It's a vast difference. And this journey that takes you from what is just a prototype to a full production model is the journey that we are going to take you on. That journey is the MLOps journey. In particular, when you deal with LLMs, it is the LLM ops journey and the prompt ops journey. So now you may say, oh, why these different terms? Why can't we just use DevOps? There are reasons for it, and I go into that in a little bit. Just hold that thought in your mind. But let us ask ourselves, what is involved in doing MLOps? Like, what will your life look like if you were to do MLOps? And what is this architecture? What are the sort of key components that come into it? There are many tools that have matured, workflows, pipelines, deployment strategies. There is Kubernetes, which of course, many of you are familiar with if you have been doing DevOps. But for ML ops, you need special things, ways, repositories to manage features that you extract from data. You need data lineage management and feature versioning. You need model management. Which version of the model? What was its performance of a given model against a particular training data set or a validation data set? What was it trained on? What data set was it trained on? And how do we know that it all works? I'm giving you a general flavor, and now we'll go down a little bit more. Then These models are beastly in size. They're huge. Go ahead.
How did you get to this documentation from the zip
We will take it. It's not easy. We'll give you instruction. At this moment, just sort of go with the flow, and then we'll take you through the steps. The whole teaching team is here, and they'll help you do it. So then these models, as you take them through training or through fine-tuning or through inference, many considerations unique to machine learning come about. Do you shard the data across the many units for training? And these are things that you don't usually encounter when you do the standard DevOps. In DevOps, let's say that you are taking a microservice to production. Usually at inference time, we are not feeding it vast amounts of data. Whatever it needs, it will read off from some database. And those are point queries usually, or very short queries. But in machine learning, often a river of data flows into these models as they go through training and as they go through validation. And vast streams of inference inputs go through them. When you try to do that, we again face a distributed compute environment. There are many compute nodes specially built for machine learning. So these are math accelerators, and then nowadays, literally ASIC chips, people are laying silicon that has LLM baked into it. Attention and transformers and LLMs baked into the silicon. So these special purpose hardware are emerging rapidly. These are extraordinarily expensive hardware. You have to, and yet no one hardware, unless you talk about something like, there are a couple of companies that take an entire wafer, do not cut it up into chips, but treat the entire wafer as one giant compute unit. In those cases, one unit can do all your computes, but usually you have multiple compute units. And so the question comes, how do you shard the computes and how do you shard the data? Because it becomes a problem in distributed compute. Now, distributed compute has been quite one of the hardest fields in computer science. It's not that easy to get it right. There are frameworks that get it right, or mostly get it right. Let's say they are all work in progress. Ray framework is one such framework. We'll deal with it. These things also come useful for inference. How do you take a model, feed it inputs, and get inferences out of it? Then comes observability, the monitoring the model, seeing whether it's performing as you expect, checking if it is getting hacked, checking whether there is model drift, data drift, being very cognizant of the metrics. And then the traditional problems of computer science. What is the response time or just system performance of your AI system? What is the scalability? For example, if you're dealing with queries, and if it is a search problem, how many searches can you yield per second in your system, amortized over, or per minute? How many queries can you handle? For LLMs, this becomes even more relevant. How many parallel queries can you handle? What is your token generation rate? These are all unique problems that need to be tracked when you deal with large language models and transformers, and in general, even the most basic machine learning models. Then comes AI security. AI security, model security, is really the Achilles heel of this subject. The more powerful a model is, the more trivially and easily you can hack it. And that is a very depressing state. It means that the more powerful a model you use, the more extraordinary measures you need to take to safeguard that model from adversarial attacks and malicious use. A typical example is, of course, prompt hacking or a prompt injection. The hello world of prompt injection used to be that once, for example, even such things like ChatGPT, which came with a lot of safeguards, system prompts and safeguards, all you had to do is write a statement, ignore everything before this line, because whatever the user said was prefaced by the system prompt, which was the safeguard. And if the last line, the user line says, ignore everything said before this line and now do this, then it would subvert all your safeguards. Well, ChatGPT has smartened up. It detects that, right? And we try to bring in security. For example, if you're dealing with LLMs, you don't want to, because LLMs are trained on all the data of the world, in it are some pretty dangerous facts. For example, LLMs know how to make a bomb. So you put safeguards that says, how do you make a bomb? And the LLM should not answer. It should say, I'm sorry, but I would not like to answer that question. You would say, who would ask that question? Actually, you'll be shocked. Questions like how to make a bomb, how to kill my spouse are actually, depressingly, as a depressing commentary on human beings, some of the most common queries that Google fields. Google has learned to deal with these, right? Or things like how to kill my boss or things like that. But the same thing, the same tooling we need to do for our AI models. Otherwise, it can wreak havoc. And so that brings in the whole problem of model security. Now you can say, if we know what are the things people search for, can't we just write a little classifier, text classifier, that will detect an input to be malicious and then not feed it to the LLM? Indeed, that is one of the approaches people take, but these approaches are not foolproof. So for example, someone apparently just fed the word bomb as an ASCII art and then said, how do you make a big ASCII art of the word bomb? And sure enough, I forget which LLM it was, but one of the commercial LLMs happily supplied the recipe. Right? Likewise, recently, Meta came up with something called Prompt Guard. It was supposed to literally guard against malicious prompts. A wonderful initiative, and to its great credit, given to open source. Till almost immediately, somebody filed an interesting bug. The bug was, remember the hello world of prompt injection. Ignore everything above this line. Somebody gave exactly that statement, but between every 2 characters, they introduced a lot of space, empty space. So I, lots of space, G, lots of space, N, and so forth, ignore. And whether humorous or tragic, it took down the prompt guard. Right? It subverted the prompt guard. And so obviously, it just shows how extraordinarily complicated it is to protect this. So if you are taking this, your models to production, you need to be aware of this. So what is the purpose of this course? What is the frame of mind that we approach this course with? I'll give you the frame of mind. Imagine that you are the MLOps team or the LLMOps team or the prompt ops team. Pick your name. The way we'll position this course or the lens through which we'll approach this course, different teams will come to you and they will say, hey, we just cooked up a wonderful model and it solves some domain specific problem. And we have showed it to our product managers. They are delighted at the results. Right? The business stakeholders are delighted at the results. Right? Now, please automate all this, take it to production, create a pipeline out of it. Because, of course, generally, our PhDs are rather averse to doing a lot of this stuff. Right? In startups, they're forced to do it. In bigger companies, they would rather hand it over to you. So that's the frame of reference. We are the people who bridge the reality between a dream and actual reality. We'll bridge that from dream to reality. MLOps is the bridge. But MLOps is not easy. And so you will notice that we'll take you through some code examples, but I would like to talk in a little bit more in generalities. When you talk of MLOps, it is actually lots of worlds intersecting. Now, about MLOps, I'll say one thing. I'm often called to advise companies, startups, a lot of them, and small companies and big companies. You hear stories. You sit around the campfire stories to share. And when you hear all of these stories, you realize that a saying of Tolstoy is very relevant here. And I'll start with that saying. It says, all happy families are alike. Each unhappy family is unhappy in its own unique way. There's a typo here, it should be unhappy. Family is unhappy in its own unique way. What it means is, in this world of MLOps and machine learning, again, as I said, it's extraordinarily common and relatively trivial to create a proof of concept. However, it is surprisingly arduous and uncommon to succeed at creating a mature and production-grade AI system and platform. And I mean it, guys. For I have seen 1 out of 100 proof of concepts go to production. The numbers are terrible. The numbers are just terrible. And a lot of it comes when you look around, the number of failed AI projects far outnumber the ones that make it to production. And amongst the ones that do make it to production, a depressing majority of them have engineers behind the scene in despair, wanting to redo large swaths of the projects, as they say, properly. They have just somehow taken it to production. And the moment they took it to production, the main thing is, oh my God, what have we done? Right? We need to redo the whole thing. So the question that it begs is, well then, how do we build a good AI system? It is not a trivial question, actually. It turns out that even very big houses like Google and Facebook and Microsoft and so on and so forth, they thought they had very mature machine learning pipelines and machine learning systems, right? Go to production AI workflows. And yet, once they got together, they formed the so-called AI Alliance, an organization called AI Alliance. The links are there. You can visit it later. And they started sharing how they are doing it. And what they found is that each of these companies had done some parts right and entirely missed out on some other part. So there was a lot of learning, even for these practically trillion-dollar giants. And with their hundreds of thousands of engineers, even they learned from each other. And therefore, an alliance was formed, which is the AI Alliance, whose main purpose is to formulate what are good practices. At the same time, as you know, AI poses a tremendous amount of risk in the world. So in US, there is a standards body, National Institutes of Standards and Technology, NIST. It makes guidelines. So they use the word AI system. And an AI system is the coming together of, amongst other things, three main components. The people who do AI, the AI hardware that you bring, and the AI the AI software that you, AI models that you bring, and all the orchestration pipeline that takes a model to production. And it's quite enlightening how they have put people first, because MLOps is above all a people-centric operation, as you will realize. It's a very odd thing to say about field of engineering, but you will see that in a moment. Now, guys, as I read this, I notice small typos, which I'll fix and repost. But this is it. It is a world in which three different worlds intersect in this ecosystem. There is the data engineering world, and we'll go into data engineering world in a moment. There is the AI researcher world, people who conjure up models, and the AI operational world, taking AI models through the processes, mature processes, and all the way to production. What do each of the worlds use? Data engineering world is something we are familiar with. It has ETL, as you know, it's a word that has been there in the industry for a long time. Data extraction, transformation, and loading into some system. Or these days, ELT, because when you have data at scale, you just bring it in, it's called the extraction, from various sources. Then you do, once you bring it in, extract and load it into your system, then you do transformation after transformation. So that is the ELT. It is also the world of traditional data governance. You need to be very careful about the data and its governance. This is particularly relevant for two reasons. One is, in AI model, you are often making predictions. You need to be aware that if your data has bias, it can lead to bias against, in the inferences of your model, you may end up with bias against the protected classes. In US, these are legal protected classes. You cannot handicap or discriminate based on handicap, based on gender, based on age, based on orientation, based on race, and so forth. So these are protected classes. You cannot say that you did not build a model explicitly to discriminate. The law is, if your model discriminates, then you are at fault. No? You should have checked to prevent discrimination. The other aspect of data governance is, to the extent that the data goes into training the model, one of the easiest ways to maliciously attack the AI system is to go and corrupt the data that goes into the training of the model. It may not have occurred to most people, but most attack vectors are internal to a company, not external. Most sabotage attempts are done by employees, disgruntled employees, sometimes just inadvertently. Somebody is in a rush, somebody takes a shortcut, and it wreaks havoc, and therefore the need for data governance. Next is data lineage and data drift, distributional drift. Let us say that you build, I'll just give you a hypothetical example. You build the weather model based on 50-year-old data. You would agree that the data that is coming in now is vastly different from the data from 50 years ago. We didn't have the glaciers melting at the alarming rate that they're melting. We didn't have the oceans warming up the way they are warming up today. And so you need to be cognizant that the data has changed, because if data has changed, the models they were trained on that data too need to be revised. So you need statistical techniques to observe distributional drift. Data privacy and anonymization is important because it's a nightmare if personally identified information makes its way into your training data. It should never happen. So we need to know mature data anonymization tools to scrub out the data. It's part of the practices. In this bootcamp, we will mention to you, in this workshop, we'll mention to you what those tools are, but we won't explicitly get a chance to do a lab on data anonymization. Nevertheless, it's worth knowing that these tools exist. And we'll introduce you to these tools. You should know they're very easy to use. Presidio is one of them. Just apply it to your data and make sure there's no PII that makes its way into training data. The next is the proliferation of different kinds of databases that we need. In normal outside machine learning, for most things, you need a relational database. If you are a little bit adventurous, you'll replace the relational database with a document database, let's say a MongoDB. When situation warrants, for a columnar database, and so on and so forth. But in the machine learning context, two particular data structures proliferate. All models take vectors as input, and a lot of models produce vectors as output, and those vectors are worth storing. For example, for semantic search and for RAG, vectors, these are called embedding vectors, are at the core of, they are the real workhorses driving those functionalities. Right? For semantic search, for RAG, for recommender systems, and for a whole myriad situation, you need to store embeddings. And therefore, to efficiently store these embeddings and retrieve those embeddings, there are dedicated databases called vector databases. We'll become very familiar with those vector databases because we will have quite a few labs using vector databases. Here, in this course, we will standardize on QDrent, which is widely used. Even OpenAI uses QDrent. So it's an open source database. But we'll introduce you to other databases too, vector databases. Now, you might say, why can't I store vectors in a relational database? See, storing is not the problem. It's retrieving that's the problem. When you have a billion, or let's say 100 billion vectors or embeddings, and these days 100 billion is nothing, think trillions. A trillion embeddings sitting in your database, you realize that if I want to do a k nearest neighbor search against a reference vector, a query vector, a linear search would be a full table scan. Right? It would be catastrophically expensive. So over the years have evolved many approximate nearest neighbor algorithms. These days, the state-of-the-art algorithm or the frameworks, and the one that we will use, one of them that is state-of-the-art, is FAS. FAS is a really massively scalable, high-performance vector indexing system. Within that, you can use different indexing technologies, different indexers. In this workshop, we will in particular rely heavily on HNSW, hierarchical navigable small worlds map indexing. But the way we'll use that is not as a AI researcher. In this course, as I said, we will just take mature vector database, QDrent, but we will know just enough about what's inside, the inner workings of it to make smart decisions and make sure that in our projects, vectors are stored efficiently. Next is graph databases. If there is another approach that is absolutely needed these days for semantic search, for RAG, for recommender systems, and for drug discovery, for many, many things, law enforcement and so forth, it is graph neural networks. Graph neural networks are creating a revolution in many fields. For example, many of you are aware of the AlphaFold, which is obviously it has many things, not just graph neural networks, but it has revolutionized proteomics and it has revolutionized material science. Lots of the geometric structure of just about every protein is now known, which was supposed to be a near impossible problem to do. And most people thought would take 100 years. So we will be doing a couple of use cases in that space. And for that, we'll need to store our graphs. So graph databases may come in useful. Relational databases hardly need to be mentioned. We'll be using one to store raw data. And analytical databases, if we get time, we'll cover it, not much. So that is the life of data engineering. That's the world. What about the AI research world? You bring in the data, the next phase is the model building. I use the word research broadly. It is very applied research in the industry. You take some models, you see whether it works for your problem or not. You fine tune it, you change it, you adapt it, then you try something else. So take it in that sense. What all things do you need? You need model stores because your model will undergo evolution for two reasons. First, data will keep changing, more data will keep arriving. To accommodate for possible model data drift, you need to keep training your model. And quite often, for the simple reason that the more the data, the merrier you are when you want to train your model on all sorts of data that you can get hold of. The second reason has to do with the fact that most of these models, the more complex they are, the more they're infested with hyperparameters. And as you go through adaptation, as you go through change, you will just change the hyperparameter a little bit. You'll need to store that model. Not just the model, you would have to store the model evaluation metrics. Right? For example, if it's a classifier, you would like to store what was the precision, the recall, the F1 score, the area under ROC curve, the accuracy, and so forth. Right? These are things that you absolutely want to do. As you enter the world of LLMs and transformers, they have their own special tools that you use to evaluate them. If you're doing RAG, for example, you'll use RAGAs. If you do working with LLMs, you would use something like, say, deep-eval. You need to not only store the model, you need to store specifically what hyperparameter values you use and what is the model evaluation metrics. So those need to be stored. These need to be computed. You need tools to evaluate that. You need to track model drift. And you need ways to mitigate that. Then, of course, needless to say, the primary task is you sit and build models. What happens if I chop off one layer? What happens if I, for example, in the very last layer, you unfreeze some of the weights and retrain the model, fine-tune the model, things like that. Or you build a model from scratch. That brings us to hyperparameter tuning. Hyperparameters are, for example, if I have a random forest, then how many trees? And how deep would you let the trees be? That's an example of hyperparameter tuning. If you're doing something as basic as polynomial regression, what is the degree of the polynomial? If you're using support vector machines, what is your kernel? Is it a linear kernel? Is it a polynomial kernel? Is it a RBF kernel? Things like that. If you're dealing with neural networks, how many layers? What's your dropout rate? Right? What's your how strongly are you regularizing it? Right? If you're using optimizers, they have parameters, hyperparameters. Now, the specific thing with hyperparameters is hyperparameters cannot be learned during through gradient descent. The optimal values of parameters can be learned of the model. For example, if you have a neural network, what are the optimal weights given a data? By training the neural network on data, you can achieve a set of near optimal weights by running through a few epochs. But unfortunately, the hyperparameters are outside the scope. Gradient descent applies only when you have differentiable functions. To ask a question, how many layers do I put in the neural network, for example? How many attention heads do I put? How deeply I stack the attention heads or the layers? What's the size of my convolutions? These are things, these questions cannot be answered differentially. Therefore, or in a very simple situation, what is the degree of the polynomial that I use for regression? What is how many trees should I grow in the random forest? How deep should those trees be? These are things you can answer, perhaps. There are naive ways of doing it through grid search. When you have just one or two hyperparameters, it is okay to do grid search. For example, you can take 10 values of one hyperparameter, 10 values of the other hyperparameter, and then you can run 100 experiments, 10 times 10. But when the number of hyperparameters in your model are something like 100, it is no more feasible. It's a combinatorial explosion. You cannot do 10 to the power 100. And what is worse, to train LLMs and large models even once is prohibitively expensive. So grid search goes out of the window, or randomized search goes out of the window. There has been considerable emphasis in this space. The right way to approach it is through Bayesian optimization techniques. It turns out that when you can't do gradient descent, right, in a non-differentiable space, all is not lost. There comes the Bayesian inference to your rescue. And you can use it. And it has been used for a very, very long time in all sorts of scenarios. It can help you quickly zero into the optimal hyperparameters for your model. Now, in the world of AI research model building, fine-tuning is a fact of life. Transfer learning has been a de facto practice, inevitable in worlds where only the scant few hyperscalers have the wherewithal to train a foundational model from scratch. Look in the mirror. Do you look like Google or Meta or Microsoft with $1 trillion in the bank? If you don't look like it, you probably can't train a foundation model, a big foundation model. So, well, life begins with not training any model at all, downloading something and hoping it will work with some prompting. If that doesn't work, you go to fine-tuning, and that already stretches your budget. But fine-tuning is a de facto step. You do it a lot. Fine-tuning is also, it is not just a practical feasibility thing, but it is the environmentally friendly thing to do. To train a foundational model consumes a ridiculous amount of electricity. It takes more electricity these days to train a foundational model than a mid-sized city consumes. Think about it a little bit. It consumes that much electricity. And I am told that the per square millimeter power consumption of these very power-hungry chips exceeds the heat of a nuclear reactor on a per millimeter basis. They run that power-hungry. So obviously, it's an environmental thing to do. Next is model training. We do it all the time. That's what we are hardly needs mention. A lot of the time, one of the practices that is growing in popularity, for better or for worse, is people use larger models to generate synthetic data. Then they take the data to train a smaller model. It's sort of a form of, it's somewhat resonant with distillation, but in a different way. It's a teacher-student approach for sure. You take the teacher to produce a lot of exemplars of how input and output should be. Output should be given an input. And then you take that and train a smaller model. So for that, you need synthetic data generation. We will learn a lot about that. Lastly, but we won't cover it here, one of the topics that used to be very important and still is but not getting so much coverage these days, is neural architecture search. As if you're building models from scratch, how do you search for the optimal shape of the model? How do you rewire it in such a way that it would be optimal for you? So that is the world of the AI researchers. That's what you keep doing day after day if you're in the core model building world. We will cover some of it, but not at a theoretical level. We'll stay very practical. After all, we are the MLOps team. Next is the AI operational world. Here, of course, this is very close to DevOps kind of thinking. You need a feature store to manage the features that you have generated after cleaning the data, after various transformations, etc., etc. It's precious. So you need a feature store. We will use Feast. You need an observability framework to keep track of the metrics. And then, of course, I'm including logging and the traditional logging and monitoring too. But you want to track, for example, if you're using an LLM, you want to keep track of what queries were sent to it, right? And what inputs, prompts were sent to it, and what the outputs were. They are considerations. Model performance metric is, of course, hardly needs to be. You need to continually monitor if there's a performance drift or degradation. You need to watch out for adversarial attack. In this course, we will put a lot of emphasis on the adversarial attack and defenses. In particular, we will use Llama Guard and Guardrails AI, both of them, and we will do some substantive lab exercises with them in our project. Then, of course, importance of benchmark. What happens is that the moment a benchmark becomes public, LLMs often tweak and they get hyper aligned to those benchmarks. So on that benchmarks, they will do very well. They'll be number one. But the moment you take them in-house and apply it to your own real-world problem on your own data, it doesn't work so well. So therefore, you need your own benchmark, internal benchmark, based on your data, your domain-specific use case. So as we do this course, we are going to do it through case studies. It's a very case studies-based approach. And I'm going to talk about those case studies shortly. But before I do that, I would like to just make an observation. See, what makes people often trivialize machine learning operation? It is actually one of the hardest things to do. And I would like to just emphasize this once again to disabuse you of the notion that this is a very easy course, right? It's made up of fun things. You will find that this will tax you quite a bit. Partly because, see, we can program away the UI, we can program away the middle layer, the database, data access layer and everything. Unfortunately, there's a dawning realization that MLOps, LLMOps, prompt ops cannot be programmed away. There is a lot of black magic here. There's a lot of mystery here. We really are working in a domain in which we know a few things, but a lot of things we don't know. Nevertheless, in a very uncertain environment, we have to build production-grade AI ecosystems and operations. And so empirical evidence, experience, and what is often called gut feeling comes in handy. Well, I am usually a very big skeptic of gut feelings, because ultimately gut is a convoluted tube with a lot of bacteria in it. But let's call it a hunch that is subliminal and you can't quantify it. It's there in your mind. You have the reasons, but you can't quite express it. And a lot of that goes into this field. You'll see that. You have competing forces. And one way, just for the sake of example, I did, and I'll explain it to you. Do you want to make the world's most perfect AI MLOps system? If you try to do that, and if you are a startup, you'll fail. Because it will take way too long. It will take way too many resources. and way too many people. You don't have. So what should you do? How should you start? First things first, you should be cognizant that you are battling opposing forces in this field. There are no perfect answers, absolutely no perfect answers. But for some problems, the problems that you are solving, there are some good answers that work. And we'll focus on those things that will work at different scale. So one fun way is to just state it using sort of constraint optimization. So, you have time. Let's take the time axis from now onwards, going to infinity. You have a model at a given time today. Tomorrow, you may have a different model because you did a different hyperparameter tuning, you did some fine tuning, or you literally wrote a new model. So your model is evolving for a given problem that you're solving over time. Your data set is evolving. Your hyperparameters, actually the specific hyperparameter values that you use tomorrow may be different from what you use today. Your infrastructure is evolving with time. More hardware is coming, some hardware is breaking down, things are happening. The performance metric that you are tracking and that means something to you is evolving over time. You would rather that tomorrow's performance metrics are better than today's, isn't it? Reliability metrics, likewise scalability metrics, and then the cost function. To have it all, where's the $1 billion? You need to worry about the cost function. And here, by cost function, we mean as in dollars and cents. Likewise, what is the time to deployment? Startups have a very short runway. You're fighting against a shrinking runway. And if you don't take off in time, there is no point having the world's best MLOps pipeline and workflow because you haven't made it. So what is our objective here? We are trying to maximize three things. We are trying to maximize the performance metrics of our model, the reliability of the model, and the scalability of the model. Right? We want all three things, but at the same time, we want to minimize two things. We want to minimize the cost of the model, the cost of your whole MLOps workflow and system. And by here, I mean the whole ecosystem. Think ecosystem, guys, think system. One of the things that I loved about MIT is they emphasize systems thinking. MLOps is systems thinking. So what does this system cost? You want to minimize the cost over time. Not just what it costs today, but the accumulated cost from now to infinity. Right? Likewise, you want to minimize the time to deployment. How long does it take to deploy? Right? Those things matter. So these are the objectives. This is what MLOps is all about. MLOps is not about, okay, I will store the features here. Okay, I'm going to use a vector database and I'm done. MLOps is being clever about maximizing your model performance, your reliability, your scalability, while at the same time minimizing your cost and your time to deployment. And that is really a non-trivial constraint optimization problem. And you have some further constraints. You want to make sure that your model, the performance of your models at any given point in time exceeds a minimum acceptable performance that your business stakeholders specify. Likewise, the reliability of a system, there's a lower bound to it. It must exceed an acceptable lower bound. Likewise, the scalability must exceed acceptable lower bound for scalability. Many companies, pager alerts go up the moment scalability goes below that threshold. These are real things. Or in the logs, you see the error rate go up. These are real things that people deal with. Also, there is a cost budget. You do want to make sure that you stay within the budget envelope of cost. your departmental budget. And at the same time, there is a time to deployment. Business may require that you deploy your new models at least as frequently as every week. If that is a constraint, your time to deployment has to be less than a week. Ideally, much less than a week, because if that deployment fails, you need to restart. You need to start another one. Those are real constraints. Likewise, the next two, it's written as a sort of a partial derivatives, and I'll just explain what it means. It means all factors being the same, over time, the performance gradient has to be positive with time, right? In other words, tomorrow's performance should be better than today. And 1 month later's performance also be better than today, right? So performance should go up, not down. Right? The slope, the arrow of performance should always be up. The arrow of reliability should always be up. The arrow of scalability should always be up. And if possible, if feasible, seventh is aspirational. Doesn't always happen, but the arrow of cost should be pointing down in the graph, right? Over time, your cost should be gradually decreasing through optimizations in your MLOps. The time to deployment should be decreasing. So you realize, guys, what the world of MLOps is when you look at it through this lens as a constraint optimization problem. Right? So to summarize, it is constraint optimization under opposing forces. Performance versus cost. You can get a lot of performance, but is it going to increase cost? As often happens, it creates its own tension between maximizing performance and minimizing cost. Reliability versus innovation. Usually, ensuring high reliability may conflict with the push for continuous improvement. Right? Quite often, if you take for example, if you're doing text classification and you start saying, instead of using BERT or Roberta, I'm going to use an LLM, the latest Llama 3.1, right? What are you facing there? It might be very accurate for a large majority of cases, but the fear is you may actually lose many things. It may not work for many corner cases. And what is worse is that your overall model reliability may go down. It's very hard to take down, let us say, a Roberta running on a small, it's a very low memory footprint. Take a LLM, deploy it, and then it's much easier to take down a big LLM simply because you may not have, you may be just at a threshold of how much that hardware can sustain. So reliability versus innovation is a continuous tension. Scalability versus time to deployment. Building highly scalable system can increase the time to deployment. Right? This is important. And this is one reason I mentioned as a startup, don't try to build the world's most scalable system. You don't have the luxury yet. Right? Likewise, data quality versus cost. Yes, you can go clean the data, improve the data quality. And many people have asked me that when they looked at some open source data, they found a very high error rate, 20, 30%. For example, when CLIP was trained, the data set that CLIP, one of the first multimodal model was trained, when people went and looked back, they were shocked at the high error rate. So were those people who trained CLIP, were they smoking pot? They weren't, or maybe they were, but most likely that was not the reason. The real reason is cost. It's prohibitively expensive to clean data, and sometimes it's not worth it. You reach a point of diminishing returns. If you remember, CLIP, the first multimodal model, or one of the first, I would say, if not the first, was literally took the world by storm. It was unbelievable that you could ask a question about an image and it would answer something. So sometimes you have to decide what is acceptable level of data impurity to go with? Model complexity versus interpretability. This is a continuous struggle. If you use a linear model, we can interpret it. A decision tree too is interpretable. By the time you go to random forest, you're losing it. By the time you reach deep neural networks, pretty much interpretability, people thought, is out of the window. Very complex models. Do you really need it? Sometimes simpler, more interpretable models do the job just as well. So it is something worth knowing. In legal domains where interpretability is important, you have to have those considerations. These days, there is a post hoc effort, explainable AI, to superimpose interpretability over black boxes. That is research in progress, and some developments have happened, but it is what it is. Automation versus control. The moment you automate everything, you start losing control, and you will notice that, and this is a continuous stress between MLOps teams and the model builders. They say that, it's very hard to take things on their own, take charge of things on their own, because they are not allowed anywhere near the higher environments like staging or production for a reason, right? Because a lot of automation is there and you don't want to disrupt the system. And so forth, generalization versus specialization. We won't go into that, but there it is. So we are trying to navigate the optimization landscape with all of these constraints. So that is MLOps. That's the real case for MLOps. Now, for me, this is appropriate. I would like to bring in one thing, which is, you may have heard me talk about this in the past, and this will end our theoretical study. We'll get into code and practical things shortly. See, in one of the most remarkable works of Galileo, and unfortunately, there are things in that work, dialogues concerning two new sciences. It literally laid the foundation of physics. Many of you may have heard this. For example, inertia is talked about in this work, and planetary motions and many things. One of the things that this groundbreaking book talked about, but we don't seem to remember, is an observation that is called the square cube law. I will simplify down what it is. You notice that if you, as a human being, if I triple your size, then your weight, assuming your volume, will triple. So suppose you are 150 pounds, it will go through a tripling. But your weight is held over your legs. Your legs have the leg bones. Now, there's a cross-section to the leg bone. That is the weight-bearing capacity of a pillar, which is your legs, is proportional to the cross-sectional area. Now, your cross-sectional area, if you triple it, if I sort of triple you, sorry, I apologize, I made a mistake. If I triple you in size, your weight will increase by cube of, actually, let me not use triplet. Let me just double. If I just double your weight, double you in size, then your weight will become cube of that. Because imagine that you are a sphere, roughly speaking. I certainly look like a sphere. Then the volume of a sphere goes by r cube. So my weight will become 3 times. 8 times rather, 2 cube, that is 8 times. But my weight-bearing capacity, which is the cross-section of my legs, cross-section area will go, area is r squared. So my weight-bearing capacity will only have doubled, 2 squared, right? It would have become doubled, right? From 2, it went to 4, right? Times. So the problem with that is 4 times. It has become 4 times now. 4 times stronger pillar is carrying 8 times the weight, which may not be tenable, it may crumble. Which is one reason usually you don't find 12-foot people, except in stories. So this was Galileo's observation. He happened to notice that different animals have different, for example, insects, they have largely exoskeletons. We have endoskeletons for a reason, right? It has many implications. In architecture, it's very much true. There is one kind of architecture that works for 2-story, 3-story building. It is suitable for that height. A completely different architecture is suitable for skyscrapers. All engineering design is about scale, right? So I would like to say that the same thing applies to our field of software architecture. Architecture is very scale dependent. You are a very small team, a monolithic architecture is fine. People wear multiple hats. The same guy who is doing the research into models is also creating the MLOps pipeline. As the scale of the team and the work increases, you need to have a different architecture and different MLOps pipeline. So I'll leave you to read this article on your own in a little bit. But what we will do is we will go through a few case studies in this course. These are the case studies we'll do. Each of them, either you will write the code or we'll give you the code. Actually, we'll give you the code of it because it's a MLOps class. The machine learning code we'll give you. But your job is to take it through the MLOps pipeline. Your job is to, for example, take it all the way to production. So the case studies you'll do in the traditional machine learning case, we have taken one example of regression, which is the California housing data set. And we have also added actually the Airbnb data set. California housing data set perhaps it's become too simple now. So we have added Airbnb, pretty similar problem. For classification, we have added the breast cancer data set. And for clustering, we are going to study a data set that I created called the Smiley data set. And you will try to cluster that data set using various algorithms. You will also do some dimensionality reduction and so on and so forth on text. So you'll get to that. For deep neural networks, we will do text clustering, but not just text clustering using a brute force algorithm. You will do it using a sentence embedding. Those of you who have taken LLM1, the bootcamp, should be quite familiar with this. If not, we'll educate you as you go along what embeddings are. Remember, guys, you don't need to know intricate details of text clustering or sentence embedding. This is not a course in machine learning or neural networks. It's a course in MLOps. So the code will be there. You have to take it through the operational processing. For discriminative learning, we are going to take text classification. So the first was text clustering. This is text classification using more or less the same technology, the same code base, but repurposed for text classification. The problem that we'll study is this text one of 3 subjects? I believe physics, biology, and something else. Right? Or there are 3 different subjects. You just have to look at a piece of text and say, which subject does it belong to? Pretty simple. Likewise, we take a problem of image classification. You need to look at the image and tell, what are you looking at? Are we looking at a house, a giraffe, a dog? What is it? So that's a classic text classification problem. We'll use a visual transformer for that. Then these are discriminative tasks. On the generative tasks, we will take 4 specific tasks. We'll take something that is absolutely hot these days. It is hard to find anybody hiding under a rock and not doing RAG. Every company that you can think of is doing retrieval augmented generation. Simply put, it is talking to a body of knowledge, or simply put, talking to your documents, chatting with your documents. We will do that RAG, but we'll take it all the way to production. Those of you who attended the LLM1 bootcamp or the LLM2 bootcamp, remember, we did not pay too much attention to taking it to production. Now we'll do it carefully. We will take a multimodal model, Lava in particular, the latest Lava, and we'll fine-tune it on specific data. We will also fine-tune a large language model to do a domain adaptation. In particular, you will fine-tune a large language model on the text of all the 500 videos of my lectures in the last 2-3 years. Then you will also do an exercise on prompt management. This is important because you change the prompt a little bit and your application system prompt and your application may break. How do you manage and have an inventory of the best prompts? If you say, well, you're going to use DSPY, now wait a minute. Your data changes, your business use case changes slightly. You need to redo the whole DSPY exercise all over again and recalibrate your so you have to maintain an inventory of prompts against inventory of AI systems. There are different prompts that work best against different LLM models. What works with OpenAI doesn't work so well with Anthropic or with Gemini or with Llama in-house or with Mistral and so forth. So one of the complicated problems is, given a use case, which combination of which prompt works best with which model? So it's a matrix. You have N prompts and M models. You can realize that it gets complicated very fast, and that brings us to the world of prompt operation. So with that, I'll come to the last topic, and finally, we'll get into the practical aspects of this course forthwith. So as I said, the one question at the heart of all of this is, first, let's build a pipeline. A pipeline is something which is a data pipeline, model pipeline, go to production pipeline. You want a pipeline that's mature and takes you through all the process. It is the backbone. It is the backbone of your entire AI system. That's why I said the backbone has MLOps, pipeline, and workflows. Into this backbone, you will plug in everything. Around it, you'll build your system. So what does this pipeline look like? That's the first question. Everyone, when people come to me for advice, practically the one question in their mind is, oh, there are so many open source projects competing with each other. There are tons of companies which are making sales presentations to you, commercial products, telling you that their pipeline, their workflow, their observability tool are the best and way better than open source. So it brings us to the question, which pipeline or workflow framework to use? Now, for this workshop, of course, we won't be touching on the commercial tools. Right? That's out of scope. And I believe that you shouldn't use those because they're emerging and disappearing. They're like Cheshire cats. They come for a little bit, they grin, and then they disappear. Right? And you have just paid a lot of money, but more than money, your architecture is now tied to a defunct pipeline or workflow. It is happening more often than you think. So stay with mature open source projects. That's the first thing. The second rule that we will say is, again, going to Galileo's lesson, we will learn from that and say, based on your team size, you are a one-man army, no framework, direct code. And we will show you a solution of a pipeline just directly with code shortly in the second half of today's session. Then there are some tried and tested pipelines there in DevOps for a very long time. You may recognize them as your familiar friends, Jenkins and Airflow. Jenkins, of course, has been there. Airflow, the good thing with Airflow is it's very Python friendly. The bad thing with it is it's Python friendly and doesn't work with the latest Python libraries, data science libraries. Right? So it's a bit of a nuisance. Then you take ML aware frameworks with or without Kubernetes and clustering. So in particular, we are big fans of MLflow. We'll take you through MLflow. It's a very mature, very good framework. And then there are frameworks which are Kubernetes or clustering aware, ML aware, and has clustering capabilities. In fact, the only way you can use them is if you do have a Kubernetes cluster. In that, the granddaddy of them all is Kubeflow. It has a maximum number of deployments out there. But recently, there has been another framework we are fond of, also gaining momentum, called Flight. The good thing with Flight is it uses, I mean, if you were to ask me in one sentence, what is the advantage of Flight over Kubeflow? Kubeflow passes data types as strings, whereas in Flight, you have strong typing. So you have less likelihood of making mistakes. We will do a pipeline using Flight also. Then there are emerging frameworks like Ray Workflow, etc. In very alpha phase, we will mention it, but we won't go into it too much. So this is the scope of this project, guys. Now, in this project, I've left some sort of empty files, and these empty files will get filled as the course progresses. But for now, we will pause on the theory part, because what I would like to do is do this. We will take these 7 use cases that we talked about, these case studies, and we will build pipeline. We will solve all of these as MLOps exercise. You are the ML team, MLOps team. 7 ML teams have approached you with 7 problems, 7 use cases. They want MLOps workflows and pipelines for all of them. They want distributed training. They want distributed inference. They want distributed fine-tuning. They want a model store. They want a feature store. They want observability. They want it all. How would you do it for each of those 7 use cases? That is what we will do in this course, in this workshop. So today was unusual. There was a lot of talking and not much doing in the first half, but let's take a pause and now we will get hands-on. So we will take a 15-minute break, and after the break, we'll regroup. And when we regroup, we will go through some demos. We will show you what a pipeline looks like in different frameworks, in Flight, in Kubeflow, in Jenkins, in Airflow, of a simple case, a few simple cases. Your job or your homework would be to fill in the rest. Now, the way this course will progress, I will be introducing a topic on Monday and doing some code lab work walkthrough, but my team will, the teaching team will, take over Tuesday, and they will go deeper into the code, the setup, the examples, and they will make sure that you succeed in the project you're doing. This course can only be successful if you follow along and if you do the exercise, guys. Otherwise, this is not an armchair course. You sit back in the armchair and listen to it. It wouldn't be of much use. Either take the case studies and do a strategic analysis. For example, in your organization, given the size and scale it is, what is the best thing to do? Which pipeline would you adopt? Would you adopt Flight? Would you adopt Kubeflow? Would you adopt Jenkins? Would you adopt Airflow? Or would you adopt something entirely different? Think through it, argue for it. We'll discuss it at some point. But for those of you who are coding, code along and let's build these pipelines. Right? So with that, I'll stop and we'll have a 15-minute break. Now, as this thing progresses, every week we'll give you a project which will be accumulative. In other words, it will be this and some more code, more tips. Some tips, by the way, in the tips and tricks section, you will notice that we have mentioned some tips. One thing that you face in the world of AI is what we call the CUDA hell. The GPU, the CUDA, never seems to work. Right? People have things running on it. They have out of memory. All the time it says it's not available and so forth. So we have put some tips here, and you will soon see we'll be putting a long list of tips. Now, project guide, how to get started with the lab. In particular, for example, how to see this dashboard, this portal itself that I'm running, right? You just downloaded it, but you're not able to run it. How would you run this portal itself? That is something that our team will now take you through. So, for example, we'll go through the basic environment setup after the break, and they'll walk you through this and some of it. But before we do this, we may do today. This particular one we'll do just today itself. The rest of them you'll do tomorrow, but we'll go through a few pipelines. We'll pipeline using Airflow, using Jenkins, using Qflow, Flight, etc. Right? So that's for the second half of the course. Let's regroup in 15 minutes at 9 p.m. Pacific time sharp. With that, I will pause the first part of this session